All right, so we want to do an example of a complete sort of ideal gas cycle. And it is similar to one that was in your homework. So it's a shape like this. So if you did 19.62 for homework, this should look familiar. The only difference is that it's not, this curve is not an isotherm, it's an adiabat. So we got the same 1000 cc starting volume. We don't know the final volume, actually. We call that V max. Call that V max. But it's the same pressure temperature combination, where we start off at 1 atmosphere and it's 406 Kelvin, right? These numbers should look familiar, and we shoot up to 5 atmospheres. So those are, got to get my units right. So pressure in atmospheres. Now, obviously, these are 1 sig fig, but let's work, let's make sure we have at least whole numbers. Let's work out to the decimal place for sig figs. I think that's the best way. No decimal places, but let's keep that ones spot significant. And so this is so this is an adiabat, and it's a process, or a cycle really, for 0.030 moles of helium gas. So it's a monatomic gas. And so this is all we need. There's a lot we can say about it. And usually what we like to do with these types of cycles is twofold. The first one is that we like to make a table of the pressure, volume, and temperature at each corner of the gas. So we got at corner 1, corner 2, corner 3, we've got the values of pressure, volume, and temperature. These don't have to be in, well, let me just say this. I would recommend that you work in Kelvin for temperature. The pressure and the volume, they can stay in atmospheres and cc's as long as this isn't gauge pressure, because when we're dealing with going from 1 to 2 to 3 and then maybe back, there's only ratios. So as long as you work in absolute scale, you're fine. The second thing that we like to do with these cycles is to construct another table, excuse me, of each process. And each process, 1 to 2, 2 to 3, 3 to 1, all have first law implications. So the heat added or removed, the work done by the system, and the system's change in thermal energy, or the gas's change in thermal energy. So technically that means we have 18 columns or cells to fill out. So these problems certainly are a lot of work, but they cover a wide range of the topics in ideal gases. And this again is the main focus for the work that we're doing. Okay, so the first row is given. So we're already 1/6 the way there. Okay, so pressure for corner 1. Oh, and by the way, what do I mean by corners 2 and 3? We're going up like this to the top. So that's 2. And then down to 3, and then back again. So this is an ideal gas cycle that flows this clockwise, and so that represents a heat engine. And I guess before we jump in and talk about all the numbers, it's helpful to get a picture in mind about what's actually happening. So I want to draw that real quick. So we have a gas, relatively low pressure, low volume gas to start. Okay, and so what do is we lock it in place and then we heat it up. When we lock it in place and we heat it up, the pressure is going to increase with the temperature. So this is 1 to 2. So when we unlock the pin, it has to have a high pressure on it. So when we start at 2, we've added masses basically. I mean, another way to think about that locking pin is you heat the gas, but you add mass so that the increase in pressure or the increase in temperature is balanced by the increase in pressure to keep the volume steady. So that locking pin, what we're really doing is adding mass as the gas expands, or as the gas is heated, so the gas stays constant, right? But then from 2 to 3, we're going to insulate the gas and remove the mass so that the temperature decreases and the pressure goes down while it expands. So this is 2 to 3. And then from 3 to 1, we are taking that now high volume, low pressure gas and cooling it back to its starting value right here. So this is 3 to 1. Okay, and so this series of processes represents the cycle that this ideal gas undergoes. I mean, the whole point of this is that you want to think about this as a piston chamber, or the chamber with a piston that's movable, and the piston is obviously going to be connected to a bunch of other stuff, right? Maybe it's connected to the turbine, or it's connected to the fan blade, or the propeller, or the the drive crankshaft, or whatever in the car. Okay, and so if we look at this process, what do? We lock it and then heat it and then unlock it and then it shoots up, and then we cool it to exhaust out the air and bring in new intake air. Right? I mean, that's what we mean by cool down, right? And then we repeat it again. We lock it, heat it, then we unlock it and it shoots up, and then we cool it, and then we lock it and we heat it, and then we unlock it, and it shoots up, and then we cool it, and this process continues. That's a single cycle. So that is a picture to keep in mind about the cycle that's actually happening. So now let's do the calculation. And like I said earlier, the first row is already given. So pressure is 1 atmosphere, volume is 1 liter technically. 1 liter might even be a better unit. And then the temperature is 406 Kelvin. 406 Kelvin. So, so from 1 to 2. So now it's just a game of which row or which cell do we fill out next. Well, the volume stays the same as it goes from 1 to 2. So we can bring down the volume. So although we have to technically fill out 18 cells, I mean, it's not, some of them are gimmies. Okay, so if the and we know that the pressure increases to 5 atmospheres. So this is a classic isochoric process, a constant volume heating. And so if the pressure increases by a factor of 5, then the temperature also has to increase by that same factor of 5. And so that's going to bring that up from 406. 406 times 5 is not that hard to do in your head. It's just 4 times 5, and then 6 times 5. 2030. So we go all the way up to 2030 Kelvin, which is like 1700 Celsius, which is really like 3000 some Fahrenheit. So this is very large, but since it's helium, helium is so inert, it's so non-reactive with other helium atoms that it's an ideal gas well into these high temperature ranges. And in fact, it's an ideal gas well into the low temperature ranges as well. It liquefies at like in the tens of Kelvin, because it's very non-interactive. Okay, so that's the second row. So that's the PVT at the top corner. Now let's work at the bottom corner. Now this is the new one, because this is an adiabatic process, and you may have seen the isothermal process when you're working that out, but this is adiabatic. And so let's kind of write some of this out. So from 2 to 3, we have gamma. Okay, when we have an adiabatic expansion or compression, that means that all of the variables change, pressure and volume and temperature all change. and we need this adiabatic ratio. This is 5/3 for a monatomic gas. Helium is certainly a monatomic gas, and so that's what we will use. And so the equations for, so we know the pressure. I guess we know the pressure returns to 1, but since the pressure since the pressure decreases by a factor of 5, that doesn't make the volume like increase by 5 or the temperature decrease by a factor of 5. They both change, but by different rates. And so let's take a look at those. So the first way to find the volume is to use the law or the expression P3 V3 raised to the gamma. It's P times V raised to the gamma, P2 V2 gamma. That's the thing that's constant, not P times V, but P times V raised to the gamma power. That's the thing that's constant. And so you can solve this for V3. You have to do a little bit of work because gamma is 5/3. And so to solve for V3, algebraically, you know, it's going to be P2 divided by P3. But then you have to take the 1 over gamma. You have to raise the equation to 1 over gamma, which for our purposes means taking the pressure to the 3/5 root, whatever that means. And so this will be 1 over gamma. And so this equation then will be 5 to the 3/2, or it's not 3/2, 5 to the 3/5. Just check. Okay, yeah, 5 to the 3, I'll get it right, 5 to the 3/2 times the initial volume of 1,000 cubic centimeters. And again, you see you don't need the volume in cubic meters. Again, an argument could be made that liters might be better, but let's just work with what we've got for now. Okay, so that's going to make, when I basically you just have to calculate 5 to the 3/5 power, which I already have calculated for you. 5 to the 3/5 power, of course, you got to make sure the 3/5 is in the parentheses. You know, if you enter in your calculator 5 caret 3 over 5, well, it's going to be, that'll just be 25 actually, because it's 5 cubed divided by 5. You got to put the parentheses in there. You get 2.626. So that's going to make the new volume 2626 cubic centimeters. So that's how you find the final volume as the gas expands adiabatically. It's not 5,000 because the temperature goes down. And how do we find that temperature? Well, we use the same type of equation, but replace the P with the T. That's going to introduce a TV gamma minus 1. You could use the gas law if you want. I mean, you could obviously do T equals PV over NR. That's fine. But I just want to illustrate the adiabatic calculations of T2 V2 gamma minus 1. And so solving for T3, now you don't need to take a root, just plug it in directly. You get T3 equals T2, which is 2030 Kelvin, times V2 over V3, both raised to the gamma minus 1, which the gamma minus 1 is 5/3 minus 1, so that's 2/3. Okay. So practice with these adiabatic problems is helpful because the adiabatic process, like I said, is really the most important process. So, and when you plug this in again, I have the answer already calculated. You get 1,063. So right here, I get 1,063 Kelvin. So that's the first cell, or that's the first table.
Due to the ideal gas law, can you not just like multiply the temperature from 1 to 3 by the same factor that you multiply the volume? Since like, I mean, kind of like we did with 1 to 2 with the pressure?
Oh, okay.
Isn't it
Oh,
just
from 1 to 3. Well, you didn't, but you don't know. Oh, so you're saying like, can we just like work backwards and just say, okay, let's just go from 1 back to 3 and keep the pressure constant? Um,
yeah.
well, then you would have, if you would have done that, it's a good suggestion. If you would have tried going from 3 back, sorry, if you try to go from 1 back to 3, you certainly would have V3 over T3 equals V1 over T1. But the issue is that you don't know either of these two. You know the ratio, and the ratio has to be um,
Yeah,
something.
and I'm thinking more of after we solve for V3.
And once you know that, that's possible. Yeah, that's certainly possible.
Okay. And I know you're supposed to use the stuff you know to be, just in case you incorrectly calculated V3,
Sure,
then you wouldn't mess up 2 answers, but
sure. Yeah, that's a possibility as well. If you see that constant pressure process, um, yeah, if you know V3, that would be another case, and that might actually give you some insight onto how these two temperatures are related and how the volumes are related, because you got 2.6, or if you got 2626 divided by 1,000, 1,065 divided by 406. If you put that in your calculator real quick, I think you actually get 2.6. So the ratios of the first and the third volumes, and the ratio of the first and the third temperatures is the same. So yeah, that's
okay.
get V3, then you can do it that way. And or you, like I said, you could also have used the ideal gas law. Um, you are forced in this problem to use the at least one adiabatic equation though.
Yeah, okay. Thank you.
Good question. So that is the table of all the pressure, volume, temperature things. So that is, in some sense, the easier table, but in another sense, I mean, this bottom table is just as easy if you know the tricks. So we talk about heat, work, and change in thermal energy as the process changes. Thermal energy is certainly a state variable, and it's related to the temperature. It's proportional to the temperature by something called the equipartition theorem, which we'll talk about after this. But calculating these values, it's almost like each one has kind of its own formula. And there's a table in the textbook. I'll put it right here. It's on page 578. It's table 21.1. If you have the e-text, or if you have some way to access that book, please look at this table, because it's got a summary of all of the, not only how to do this table, but also a summary of the heat, work, and change in energy for each process. And so let's go through those processes kind of in this third column over here. Let's starting with 1 to 2. 1 to 2, and for many of these processes, you might find that one of those cells is 0. And indeed, from 1 to 2, you have that the work done by the system is 0, because it's a vertical line. There's no area under a vertical line. And so that's an easy way to start right here. So now we just have to do the work, to find the heat of the change in temperature. So the heat added from 1 to 2, that's a Q with a 1 arrow 2 subscript, equals the number of moles times now the molar specific heat at constant volume times that change in temperature. So that'd be T2 minus T1. And so working that out, you get 0.03 moles, that was given, times 3/2 R, that's also given for a monatomic gas, I'm going to run out of room, times 1624. So let me just move it back a little bit. 0.03 times 3/5 R. The change in temperature from 406 to 2030 is 1624 Kelvin. And with the gas constant and the moles there, I'm going to get that the change in, I'm going to get that the total heat added in that first process is 607 joules, 607 joules. And how this one check, there's several different checks you can do on this table. The first check is that Q minus the work done by the system has to equal the change in thermal energy. In chapter 19, we did change in thermal energy equals Q plus the work done on the system. But for these problems, it's more useful to consider the work done by the system. They're equal and opposite. It's a Newton's third law thing. I mean, and so what this W sub S represents, since there's a minus sign right here, the W sub S represents the actual area under each of these curves. And so it's the area, with respect to the direction at which the curve is going. So there should be a positive integral for the area from 2 to 3. There should be a negative integral from the integral from 3 to 1. And we can go over that. Okay, so that's the first, and then of course the first law has to be valid. Okay, so that is the first row. Second row, once again, we're lucky to where the second row is adiabatic. So that gives us a 0 heat, right? Remember, the adiabatic process is something that occurs so quickly that heat doesn't have time there's no time for a heat transfer out of or into the system. And so we model it as being completely insulated. So that means that we're going to have and this is what we've got, we're going to have a positive work done and a negative change in thermal energy. So how do I calculate that? I need, I need to use the work equation for the adiabatic process, or I would just do change in thermal energy. It's for any gas process, the change in thermal energy is equal to the number of moles times its specific heat at constant volume times its change in temperature. So that's true for any ideal gas process. It's actually true for any, it's true for any gas. So we'll just stick with that for now. There's a reason why in chapter 20 that has to do with an important result called the equipartition theorem, but let's just take it as kind of hypothesis for now. Because the equation for work for an adiabatic process could be kind of confusing and it's kind of hard to see where it comes from. So I would rather just do this. So the change in thermal energy for this process is 0.03 moles times the same times the same 3/2 R. Now the change in temperature from 1063 to 2030, well, from 2030 to 1063 is that the change in temperature is what? It's 1060, right? Because if you have 1063, the change in temperature is like 960 or so. To look at that real quick. So 1060 plus 1000 is 2063. So subtract 33, it's 967. So the change in the temperature from 2 to 3 was minus, where am I at? Okay. Minus 967. So that's what I'll put right here. It is a minus. It's not forbidden to use Celsius for these heat problems. In fact, sometimes that's how the units of specific heats are defined. I would recommend when you start with Kelvin, because you have to use Kelvin for the gas log table, use it also for the heat as well, because you get the same answer. So this gives us a value of, I think, 361 joules. I can double check that real quick. So yes, that answer is 362. And making sure we get the minus signs right here, the energy, so we get 362 joules of positive work. And the energy of the system goes down by 362 joules of work. And hopefully that should give you some reflection about the first law of thermodynamics, because what's happening is that the system did work, right? The piston is connected to whatever it's connected to, the fan blade, the propeller blade, the engine, and we got a useful amount of work out in this step. And so the useful work that we get out comes from the energy of the gas going down. So hopefully that makes sense. But there's a, you got to make sure these signs make sense to you. There's a Q minus this positive number equals the negative change in energy. And then so for the last one, for the last table, we don't get a freebie. We have to do all these straight up. Fortunately, they're not hard. So we can just do them. So now let's go from 3 to 1. I think the easiest one to start out with, if it's a constant pressure process, is to do the work. The work from 3 to 1 is the pressure, that constant pressure, times the change in volume, V1 minus V3. And now we do need to convert to SI units to get joules. So this is 1,000, this is 101,300 pascals times the change in volume, which is 1,000 minus 2626, which is whatever that is. But in SI units, it's 0.01 minus 0.002626. It's not 1626, I checked. So it's, when we do that, we're going to get so we get 101,300 times 0.001 times or minus. And I'm doing it in a computer algebra system. 626. So when I do that, I get an answer of, minus 164. So I get minus 164 for the work done. That is a negative number. So, minus 164 joules. Because why does that make sense? It's because you have to do work on the system to get it back to its starting position. Remember, this gas just shot up. It did work on the environment at the expense of losing its energy. And so now the environment has to do work back on it to bring it back to where it started. But fortunately, the environment does less work to bring it back to its starting point than the amount of work that the system did on the environment, right? And so that's the basic idea behind an engine, is that you add in a certain amount of heat, you do work, you do a little bit more work to get it back, you do negative work to get it back, but you have this difference in work. You have this net work that you got out of the system. In doing the heat from 3 to 1, I'll do it right below here, heat from 3 to 1. Now we use the constant pressure, specific heat. And doing that, we're going to get number of moles times now 5 halves R, because it's a constant pressure process, monatomic, times those change in temperatures, T1 minus T3. And when I do that, I get, I believe I get 414. Yeah, 415 or so joules. Let me just double check that. It's actually 409. So let me put that right here. So we lose 400, so we had to cool it. So 409 joules of heat transferred out. We had to do minus 164 joules of work. So if you look at this final cell here, it's minus 409, but that is minus a negative 164. So it's 409 plus 164, and we get that 409 minus 164 minus 164, 245. So that's a minus 245. Okay. And so that completes the two tables that we wanted to make. Of course, that's only the beginning, because we want to think about what these tables mean, why we're actually calculating these tables. Okay, you can certainly come back and check the math on all these things. There's plenty of checks that you can do on this bottom table. Arguably, this one is more important than the first one. And it's certainly dependent on the first one. The change in thermal energy should add to 0. And indeed, if I do that here, 607, oh yeah, if I do 607, yeah, it actually works out. With that rounding error, I actually get 0. Okay, so what does that mean? That the change in thermal energy is 0. Well, it means that the temperature should go back to where it started. And of course, if you think about a car engine, right, it intakes air, and then it, does what it does. It compresses the air and then lights it up. So lights up the fuel inside, so the air shoots up, the gas shoots up. And then as it's being, what do we mean by cooling, right? There's some, valves or something that open up and take the air out, the air with the combusted fuel, like the CO2, the empty remnants or whatever, out into the exhaust. And while it's exhausting that air, it's intaking new air. And so you start the process with the same initial temperature. So a closed cycle always needs to repeat itself, and so that way the temperature starts at 0. Okay, so I'll even kind of running out of space. And this is kind of getting into some topics from chapter 21. Trying to think where I could write it. Maybe I'll write it up here. I'm going to write it in the upper right-hand corner. So the change in thermal energy, the change in thermal energy has to be 0 of the cycle total. Maybe even to, it's 0. The total change is 0. Also, the work done. If you add up back down here, if you add up the work done, including the minus signs, you're going to get what we call work out. This represents the amount of useful work that the system did while you were heating it, and while it was expanding, and while you were pushing it back, right? So in this process, the gas shot up, but then you had to cool it, so the environment had to push it back down. And so when you add this number up, what do we have? 362 minus 164, that's 198. And so 198 represents, graphically, it actually represents this area under the curve, or not under the curve, the area inside the closed curve. That's the amount of useful work that was done. And so we can, so we could summarize that as well. So we get the work out is a positive 198 joules. Now, what about the heat? Well, we're not going to add the heats. We're in fact going to add only the positive parts. The positive heats all represent the total heat that we added to the system. And all the negative heats, which we call that Q sub H. So in this case, Q sub H would be 607. So we made a heat transfer of 607 joules. We got, of the 607 joules, we got a useful 198 joules of work. To that end, we also had to exhaust out amount Q sub C. And that's the magnitude, that's the absolute value of the negative stuff, all the negative stuff put together, which is, for our purposes, B409. Once again, the next check then is that the heat that was added, the 607, part of it goes to work, part of it goes to exhausted out. And the book has these like engine type heat engine diagrams, which are a little bit more detailed in chapter 21. You can go through it. But so that's for a single cycle. Now, if you repeat this over and over, you can turn all these joules into watts, right? And if you do this fast enough with enough turbines, with enough cylinders, then the watts can turn into horsepower, and you can get an estimate on the horsepower of your engine. So really the last remark to say about this topic then is that we define something called the efficiency of the engine. And the efficiency of the engine, it's the useful work that you get out minus it's the useful work that you get out divided by the heat that you put in, right? It's what you get divided what you pay. That's what the book likes to say. And for this gas, it's I guess I'll go down to the bottom now. Kind of seal off this last corner here. The thermal efficiency is Greek letter eta. Like I said, it's defined as the it's defined as the work that you get out divided by the heat that you put in. And for our calculation, you get about 26%. That means this engine is 26% efficient. Okay, the book, goes through stuff about, it goes through stuff about engines and efficiencies and stuff, but that's how you calculate it. I'm going to certainly save this figure. So this is really a complete, full-blown analysis of an complete ideal gas cycle, starting from an initial state, undergoing two or three or four processes, and then returning to its initial state. All of those closed cycles have what we call an efficiency, and you can use these tables to calculate those things. So yeah, this is a really good opportunity to practice all of the different pieces of thermodynamics.